Hi everyone, and welcome to our video on scientific notation, units, and unit conversions. All right, so real quick, I want to talk about the base units that we use in physics. If you're familiar with the SI system, a lot of this should look familiar. We'll use the first three very often. So meters, seconds, kilograms, those are like the three ones that are really important. But as we go through the year, we'll also talk about newtons, joules, and watts. As you can see, those are for force, energy and work, and power, respectively. Scientific notation you might be familiar with. If you want to convert something, we have to move the decimal over. And so if the decimal was here, then we have to go 1, 2, 3, 4, 5, 6. So if we're moving the decimal 6 times, then that's going to be our exponent. And we want a number that's in between 1 and 10. So I'm going to put my decimal here. So I'm going to end up with a number that's 5.6. And then my exponent is 6. Okay. Now, similar idea for numbers that have decimals to the left. We're just going to move that decimal 1, 2, 3, 4, 5 right there. Again, making a number that's in between 1 and 10, or at least that first part of our number is in between 1 and 10. So it's going to be 7.8. And then our exponent is just how many times do we have to move the decimal. And the negative here just represents that we had to move it. Moving the decimal to the right means that our exponent is going to be negative. Now, scientific notation will show up a lot if we were talking about like the charge of an electron. Charges of electrons are really small. They're 1.6 times 10 to the negative 19 coulombs, right? Or if we ever talk about universal gravitation, we might talk about the mass of the Earth or the mass of the sun, which, the mass of the sun is 2 times 10 to the 30th kilograms. So obviously, dealing with scientific notation is sometimes easier than dealing with 30 zeros at the end of your number. All right, and then real quick, I'll give an example of what to do with scientific notation when you're multiplying or dividing. I mean, honestly, you can just kind of plug it into the calculator and it usually spits out the correct number. But one thing you have to watch out for calculators is watch out for order of operations. Make sure that you use parentheses. And it might be good to just like write out your steps to kind of check your work. I've seen lots of students make mistakes because they plug into the calculator and the calculator does things a little bit out of the order that they expected and they get the wrong answer. So anyways, real quick example. And one thing to kind of watch out for is when you are doing some math here, look out for your exponents. Right? If you're multiplying, then the exponents should add. And if you're dividing, then the exponents should be subtracted. So you should take a look at your exponents to see how far off are they from what you originally put in. So for example, if I'm multiplying these two numbers, if all I was doing was multiplying these two, a quick look at my numbers here. I know that my exponent should be somewhere around 8 because I have a 12 and I have a negative 4. I know that when I'm multiplying these numbers that my exponent should be 8. Now it really depends on the number in front if that number, exceeds 10 or not. But even if I was like dividing, let's make this a multiplication and division example. I'll kind of show you some steps that I would take to kind of check my work here. So as I said, I'm multiplying the numbers in front. So 2 times 3 is 6. And then my exponent is 8. My denominator hasn't changed. And again, looking at my exponents here, I have an 8 and I have a 7. So I know that my final answer should have an exponent pretty close to 1. And that's exactly what it is in here. So 1.5 times 10 to the first is just 15. And we're done. All right, and then one last thing here is how to convert numbers, or sometimes called dimensional analysis. I'll do a real quick example, like an easy one, centimeters to meters. If we're going to do this in a formal dimensional analysis way, let's say we have like 5.2 centimeters. And doing this as dimensional analysis, I'll multiply it by the ratio of how many centimeters are in a meter. And I'll put the centimeters on the bottom, right? Because I want these numbers to cancel out. So when I set it up like this, centimeters being multiplied at the top and then centimeters being on the bottom down here, those cancel out. So all I'm left with here is meters as my final number. And this really looks like 5.2 divided by 100, which just becomes 0.052 meters. All right, that one might be kind of easy. If you're interested in light and light waves, you might know that visible light is somewhere on the nanometer level. So like a blue wave of light can be somewhere around 400 nanometers. But if I'm doing some math, I might want to convert that to meters. So I want nanometers in the denominator. And there's a lot of nanometers in 1 meter, 1 times 10 to the ninth. But again, the way I set this up, I have nanometers being canceled out, and I'm really just taking 400 and I'm dividing it by this very big number of 1 times 10 to the ninth. And that really just comes out to 4 times 10 to the negative 7 meters. Okay. Finally, one that's a little bit more interesting is miles per hour to meters per second. So we might be familiar with meters per second. We might be more familiar with miles per hour, but meters per second is what we typically use in physics. So let's kind of see an example of that. So we have, let's say we have 75 miles per hour. And actually, I'm going to write this so that it's a little bit more intuitive. I'm not going to write mph. I'm actually going to write it as a fraction. So I have miles, and then I'm going to put hours in the denominator. All right, now if I want to convert this, the first thing I want to do is I want to get rid of my miles and convert that to meters. There's 1,609 meters in 1 mile. And then I want to set this up where I get rid of hours. Now notice that hours here is in the denominator. So I'm going to, if I want to cancel that out, I have to put hours in the numerator. And I know that there's 60 minutes in an hour. But I don't want minutes, I want seconds. So I have to do that same thing again. I could do 1 minute is equal to 60 seconds. Okay. So finally, if you kind of just follow along here and look at like what's going to be canceled and what's not going to be canceled, let's maybe just put this in a different color here. So we have, let's see, we have hours and hours canceled, minutes, minutes canceled, miles, miles canceled. And what we're left with is meters and seconds. So I have meters in the numerator, seconds in the denominator, and that's what my final answer is going to be in. So if I did this math, this comes out to 33. Actually, really, it's 33.5 meters per second. But really, I'd probably just write this as 34 meters per second if I'm trying to be consistent with my significant figures. Okay, and then these are just some common conversions I think are really useful. So 1 kilogram is 2.2 pounds, and 1 meter per second is 2.23 miles per hour. I really like this. I really like the fact that we have a 2.2 here and a 2.2 here. That kind of makes our life easy if we're ever trying to convert from one to the other. And then some common ones that I'll use in some of my problems here. So typical person in your class, I don't know, I shouldn't say typical because, you know, people have a variety of weights, but a typical male in high school might be 150 pounds. 60 miles per hour is a common measurement I'll use. You know, if you ever hear about a car going 0 to 60, so I might use that number. And then 100 miles per hour, I do like to use baseball examples. And so some of the hardest baseball throwers are throwing about 100 miles per hour. So these are some common numbers that you might end up seeing in your problems. All right. And I think I'll stop there. All right. Next video will be on trigonometry.